Simon, or I go by Alex. And today I'd like to talk to you about part 2 of our talk, which is constructing extreme mass ratio waveforms from harmonics. So today I just want to give a quick outline. First I will talk to you about EMRI orbital frequencies and a definition of gravitational waves. And then I'll talk to you about some math behind how we calculate gravitational waves, our data structure, interpolation techniques. And then I'll show you some example waveforms that we have actually made and some future work that will be done. So first to talk about inspiral orbits. Talya talked about this previously of how we actually calculate inspirals given fluxes. And in this research that we did this summer, we focused on equatorial eccentric orbits, which are when theta is pi over 2. I have included a graph of spherical coordinates just in case anybody forgot about those. And then this graph right here is a top-down view of the z-plane. So this is just in the equatorial plane. And we see that there are 3 orbital frequencies that contribute to the gravitational waveforms. There's omega r for radial motion, omega theta for polar motion, but this is going to be 0 for equatorial plane, and omega phi for axial motion. And talking more about the frequencies, we see in this graph here that far away from the black hole in the weak fields approximation, all 3 of the orbital frequencies are constant, so they approach the same value. There's no difference in between them. This is the Newtonian limit and what we see in Kepler's laws, which say that orbits form closed ellipses. So you can only start and end at the same point if all 3 frequencies are the same. But we see that in the strong field regime, so close to the black hole, these frequencies diverge from each other and can be quite different. And this is what we want to observe because that is where we get the most interesting and rich waveforms. So talking about gravitational waves, they are so defined as disturbances in space-time, which, as the name implies, propagate as waves. And in the EMRI instance, gravitational waves are created by the small black hole interacting with the strong field of the supermassive black hole. And this is on the order of 0.1 to 100 millihertz. So as Talya described, would not be in the range of LIGO, but will be detectable with LISA. And then we can use these gravitational waves to map strong field black hole spacetime near the merger. And this leads to a lot of interesting physics. So we can measure the black hole properties for the supermassive black hole, basically analyzing the gravitational wave to find the mass and spin of the black hole. We can also test the nature of the black hole gravity, so either if the gravity is explained by general relativity or if there are alternative theories that explain it. And we can also understand the types of objects at and near the centers of galaxies. So I've included a little video. This is just a model of an extreme mass ratio inspiral, and it has the orbit and shows the gravitational waves that can be created by the inspiral. So talking a little bit about the math, this is kind of a large equation, but the genesis of it is that using the wave equation, we can say that any wave can be broken up into a superposition of sines and cosines. So this could be seen here using the frequency domain Topolsky equation for gravitational waves. It's that h of t. And all this is a pretty dense equation. Basically, you have h lmkn, which is a complex amplitude. And then we also have a spin-weighted spheroidal harmonic, which also contributes to the amplitude. And you also have complex phases. And we see that embedded in that is omega mkn, which contains the orbital frequencies that I introduced earlier. Because this is, again, only on the equatorial plane, omega theta is 0, and so we can choose k is equal to 0. And then, because it is very computationally difficult to get from negative infinity to infinity, we only choose the n value large enough to get a resolved waveform. So this happens to be around -10 to 10 for low eccentricity and around -30 to 30 for high eccentricity. And then talking a little bit about our data, we get the values for the complex amplitude and the orbital frequencies in large HGF5 files, which is a binary file because there are so many data points in our grid. And we have one file for each supermassive black hole spin A. And A is from 0 to 1. And so basically what we do is for each mode, LMKN, we have a grid of P, E, and cosine I, whereas again in the equatorial instance, cosine I is just 1, so we just get a plane. And for each grid point, we have values for the orbital frequencies and the complex amplitude. And so in our Python function, we actually have a function that picks out values only for a certain mode, and then we add all of these modes together as voices, again, the sines and cosines that contribute to the full gravitational waveform. Now to talk a little bit about going from the Inspiral to the waveform. From Talya, say we get a world line of P and E values for all time of the Inspiral. And we have, this is just for a singular mode, a grid of P and E values. And what we do is interpolate along each end slice, and that will make sure that near the last stable orbit we don't go off the grid, as we would if we just interpolate in, say, P. And so we go along the end slices and calculate the amplitudes, frequencies, and P values for each end slice for all E of T. And then after that, we interpolate again for all P of T, and that is how we get the waveform along the specific world line. And again, we do this for each mode and add the specific waves together to get a full gravitational waveform. So now looking at specific examples that we have calculated, this is the Schwarzschild case, so when the supermassive black hole is not spinning, and for initial p-value of 10. And I put two waveforms side by side, one with an eccentricity of 0.1 and one with an eccentricity of 0.5. And we see already there is a huge difference in the waveform. So the second row right here is at the very beginning of the Inspiral, so when they're around the same p-value. But we see that the lower eccentricity has a lot less amplitude variation than the higher eccentricity. But then we notice that at the very end of the waveforms, that's this last row right here, the waveforms start to look a little more similar, and that's because it's deep in the strong field where the eccentricity has kind of upticked a little bit, and because the orbit is really close to the black hole at this point, the strong field physics is fairly similar between the eccentricities. Looking deeper into this one specific case, again, we're looking back at the beginning of the Inspiral. We can already deduce the orbit of the small black hole around the big black hole based solely on the gravitational wave that we see. So we predict that the lower eccentricity orbit looks something like this, where because the eccentricity is more circular, it stays pretty far away from the small black hole at the beginning of the orbit, and so that leads to the less amplitude variation. Whereas the larger eccentricity looks more like this orbit, where it has a very large eccentricity, so at one point it gets fairly close to the black hole, and that's how it gets kind of roped in and then goes back out. And that's how you see the large amplitude and quick frequency gravitational waves before it goes out into larger radii again. And I'm looking at a Kerr case. This is for A of 0.9 prograde, so that is when the black hole is spinning in the same direction as the orbit. And this is at a higher eccentricity of 0.6. And we see that it's fairly similar to the Schwarzschild case. This is at beginning time and late time, and we see that, again, with a higher eccentricity, you get that very high amplitude variation at the beginning. Though we do see that at the end time of the waveform, the variation in the amplitude has smoothed out quite a bit more than the previous case. And this is due to the fact that in Kerr black holes, the last stable orbit is closer to the black hole than in Schwarzschild cases. And so that gives more time for the orbit to circularize. But we do see a new feature in the Kerr gravitational waves that we don't see in the short shield. And that is in this middle graph, you see that there are beat frequencies. And that is due to the black hole having spin. Now to talk a little bit about the future work, there are some things that we can do right away, such as parameterizing in a 3D space. So this is adding inclination to get to generalized orbits. And then we can also look at special EMRI cases, such as the down horizon flux, as Talya mentioned. And say if the small body has spin, that will also affect the waveform. And we also have resonances for orbital frequencies. So looking at generalized orbits, you see that since we add inclination, we, one, have one more dimension in order to interpolate in, so that will be harder to interpolate. But we see that because of inclination, we have a theta, omega theta contribution, so there will be richer waveform structure. And then going into small body spin, although we haven't fully calculated this, this is part of Lisa Drummond's work, we do predict that there will be precessions from the Inspiral due to the small body having spin. So this is just a model. This is in no way real data, but this is just kind of a prediction of what will happen, where there will be oscillations around the world line. And we want to see both how this actually affects the Inspiral and how it affects the waveform. And then finally, there is a prediction that when the orbital frequencies have small integer ratios, for example, 3/2, there will be resonances that are due to the fact that tidal effects from other objects in the vicinity of the EMRI won't average away. So that is because the orbit will spend more time in certain positions than in others in the parameter space. And we predict the Inspiral have some jump, but we have not yet calculated how strong this effect will be or how it affects the waveform. So in conclusion, we have some solutions to gravitational waves, but there's definitely a lot more physics and research to go into this. Thank you.
Questions?
Yeah.
Hi. Are you considering the orbiting objects as mass point?
So no. The adiabatic approximation that we use has the basically you have the supermassive black hole, and then there's a point particle, which in our case, the adiabatic approximation assumes that the point particle has mass, and so that will actually affect the space-time, and that's how we get the Inspiral and the gravitational waves, is from assuming that the test particle actually has mass.
So is it a point? I was wondering if there is a possibility that the orbiting objects collapse due to the tidal force of the supermassive black hole.
In our instance, we don't assume that. We do assume that it would stay just a, I guess basically, yeah, a singular point, just a point that has mass. But yeah, we don't assume in this case that there are going to be any effects on the small body.
Thank you.
Mm-hmm.
Yeah, go ahead.
I was going to say, yeah, it can't be a point particle in GR, because then there are contradictions. So it's a small particle.
Any other questions? I'll ask you a question.
Okay.
So in the first movie, you said how you showed an animation. I noticed that the inclination of the orbit was changing quite a lot.
Right.
Is that real effect or is it just an animation?
Yeah. So this is actually a real model that was made by Scott Hughes and I believe Steve Drasko. And so yeah, this is an actual instance of the case, and this is just a high eccentricity orbit. So that's why it goes so far out, and then gets kind of pulled out. Yeah, and the inclination is also changing quite a lot. Yeah, there will be whatever inclination it starts at, there will be kind of a precession around. So you have whatever inclination above and below the plane.
So that means in order to do this correctly, you definitely would have to include inclination. Right?
Yes, yeah. So we assume that in most cases, this small body will actually have some inclination. So when we assume that it's in the equatorial plane, this is mostly just a starting case. And yeah, definitely in the future we'd like to have generic